Okay, so let's look at a molecule where we had to think about an E2 reaction, which of course means anti-periplanar, right? You get things anti-periplanar. So one of the things we'll have to do probably is rotate about sigma bonds sometimes to do this. So
if we get a stereochemistry like Superon, like how is that? Is that
I like to think of such scenarios. I believe in you. I believe in you. We were recording there, right? No, thanks. So yeah, don't get it wrong. So yes, if you screw up the drawing, that's one thing, but make sure you tell me. If it's SN2, you can say this stereochemistry should be inverted. At least that way I know you have an idea what's going on, right? Okay, but for this one, you needed anti-periplanar. So you needed the leaving group, Br in this case, and an H 180 degrees apart. Right?
Why does it have to be anti-periplanar?
Why does it have to be anti-periplanar? Let's get an anti-periplanar conformation and then see why.
Is it already in here? Yeah, isn't it already? Yeah, it's already in one.
It is. It is an anti-periplanar conformation, but I don't like drawing it like having it like this because this makes it hard to decide if it's cis or trans. Right? So this makes it hard to see cis because right in E2 or E1 reactions, those are stereoselective, right? Would they rather select for E or Z? E, right? So I think it's easier to get things in the right conformation to see that, the easiest way. But if you don't want to, if you can see it, by all means go for it. I can't. Right? I literally can't. So I have to rotate. I'm going to rotate one at a time. So if I said this is carbon 1, this is carbon 2. We have two beta H's over here. Right? I'm just going to go with those H's. Obviously there's beta H's over here as well. But I'm just going to stick with these for this problem. So I'm going to rotate to get one of these H's up here. So literally draw it the same, put an H here, wedge, and a hatch. So one H is going to go up, the other H is going to go back, and the methyl is going to come forward. And I could have done it the other way, absolutely. Right? And this Br, this carbon 2, as I have it labeled, didn't change at all. Right? So I'm going to rotate again. This time I'm going to rotate carbon 2 to get the Br to be in the plane. So I get the Br in the plane. Br would be here. The H would now be going back. And this ethyl group would now be coming forward. Right? Carbon 1, carbon 2. So now they're H and the Br 180 degrees apart. I like them to have in this conformation because now I can tell this methyl and this ethyl are on the same side of the forming alkene, and this H and this H are on the same side. This makes it easier for me to see the forming alkene. Right? Now, why anti-periplanar? Right? So to do an E2 reaction, you need to get the leaving group bond to break, right? You need to have the carbon-bromine bond break. What's the only way to break a bond? Put electrons into the sigma star, or the antibonding orbital, right? Well, where is the sigma star after this? The sigma star is 180 degrees away. So it has to be lined up perfectly as, say, right? So because these two electrons, right, in that CH bond are going to go into that sigma star. Right? As this H is being taken away, these two electrons go to sigma star. That breaks this carbon-bromine bond. Right? So that's why it has to be lined up that way. Because to break that carbon-bromine bond, where sigma star is at, it's 180 degrees away. So we need to get these electrons lined up so they can go perfectly into sigma star. And you can actually kind of see this looks like a pi bond. Right? A face-to-face pi bond. You can kind of see it. Alright, so now I draw my alkene, and like I said, the reason why I like to get it so the H and the Br are in the plane and not wedged and hashed, because now it's really easy to see that this methyl and this ethyl are on the same side of the alkene, and that this H and this H are also on the same side of the alkene.
So what if you flip?
So now, so now let's analyze this. So this is one possible product, but how many beta H's do we have over here? 2. And so I just drew one version of this. And what kind of version is this? This is an alkene? Is it E or Z? Z, right? This is the Z. So if I did the other H, if I did this H and rotate it up, I would make the E product, right? Do I need to show that, or can I just tell you what the E product would look like? Can you see that? It'd just be rotating this one more time and doing the elimination. But it makes so that this methyl and this ethyl are on opposite sides. Right? So the other product would look like this would be the E product and Z product. And which product would be more likely to form? The E. Because of? Sterics. Good. Okay, so let's do a cyclohexane ring. And let's start off with it in 2 dimensions. I don't know. Make this. Somebody pick a molecule or an element.
Oxygen.
Pick a better one. Pick a better one. Pick a non. Fine. Putting tungsten on there. Why not? Don't worry about it. All right. So we have this molecule, a 6-membered ring, that we need to draw and translate this to a chair conformation. So the first thing you need to do is draw a chair conformation. Also, what I would do is go back to my cyclohexane and number those carbons. 1, 2, 3, 4, 5, 6. And you could say 1, 2, 2, 3, 4, 5, 6. Now, some people get confused when they draw these chairs. What I always do is I go to the top point here, and I know that one of those has to be axial up. So I just draw axial up, equatorial down. Then the next carbon over has to be axial down, equatorial up. Axial up, equatorial down. Axial down, equatorial up. Axial up, equatorial down, axial down, equatorial up. Right? Notice I haven't put anything on there, but at least I have all the bonds in the right places now. Right? So carbon 1 has a methyl group on it, and it's on the top part. It's pointing up. So I'm just going to put that right there, pointing up on carbon 1. Carbon 2 has a bromine pointing up. So is the carbon 2 is a bromine going to be axial or equatorial in that case? Has to be equatorial. Good. The tungsten is pointing down. Is that going to be equatorial axial? It has to be pointing down. It's on the opposite side of the bromine. The bromine is pointing up or down here? Up. So that means I put the tungsten down. It's on the opposite side. Good. Good, W. Right? Let's see carbon. We skip carbon 4. Carbon 5 has a ethyl group pointed up. So is that ethyl group going to be axial or equatorial on carbon 5? Axial. Everybody see that? Everything else is just H's. Fill these guys in. Lots of H's. Stupid H's. So that's step 1. You gotta draw it, right? Take it from a cyclohexane that's like this, get into a chair conformation. That's the first step. The second step is, if we're going to do, if I said in the problem, I said this is going to be an elimination. You have to do an E2 elimination. Right? This is going to be an E2 elimination. You need to get the leaving group to be in what place? Can it stay equatorial, or does it have to go to? Has to go axial, right? We have to get it to axial. We have to get the leaving group axial. So right now it's equatorial. But the bromine's pointed up. Is it always going to be pointed up? Yes. Whether or not it's on top or bottom of the ring never changes. Because you can be equatorial and pointed up, and you can also be axial and pointing up, right? So whether or not you're on the top or bottom of the ring doesn't change at all with that. So we're going to do a ring flip. So what happened was carbon 1 went down, carbon 4 went up. So I labeled this as carbon 1, 2, 3, 4, 5, 6. Right? Again, let's go through the exercises. So the carbon 4 here is at a top point. Let's draw axial up, equatorial down, axial down, equatorial up, axial up, equatorial down, down, up, down, down, up, right? Now, like I said before, if you were on the top part of the ring here, the methyl's on the top part of the ring, where's the methyl going to be in the other side? Is it still going to be on the top? Has to be up still. Never changes. If it's up, it's always up. What will change is whether it's axial or equatorial. It's always going to be up, right? It's always going to be up, right? So on carbon 1, the methyl group is up. So on carbon 1 here, is the methyl group going to be axial or equatorial? There it is. On carbon 2, the bromine is pointed up. Is it going to be axial or equatorial? There it is. On carbon 3, the tungsten is pointed down. Is it going to be axial or equatorial? Tungsten. Carbon 5, the ethyl is pointed up. Is it going to be axial or equatorial? Equatorial. Everything else we fill in with H's. Good. So now notice, now we look at our leaving group, bromine, and we see what else is axial next to it. It's a beta hydrogen. So notice the hydrogen on carbon 3 is a beta hydrogen to this bromine, right? Everybody sees that? There's going to be a beta hydrogen here. The problem is this hydrogen is not trans, or it's not trans to it, right? It's not trans diaxial. It's not antiperiplanar. It needs to be, right? The leaving group needs to be axial, but so does the hydrogen that it's taking, that's also leaving. So this hydrogen is not axial. Can it be eliminated then? No. So only one possibility is available, and that's this hydrogen. So where are you going to put your double bond at? Between carbon 1 and 2. That's the only place you'd have a double bond in this molecule from E2 elimination. Now, let's say, sure. Negative nitrogen. I'm going to flatten this back out.
So why do you sometimes put in sigma star bubble, but sometimes you don't?
I just started putting sigma star in this year. I'm not used to it yet, but I should. You could. Either way is fine. So the double bonds between which two carbons? What we say? 1 and 2. So the tungsten still has tungsten's still there. Oops, that's more than a W. Ugh. Tungsten, and our ethyl is still opposite side of the tungsten. We number our carbons 1, 2, 3, 4, 5, 6. Do we see that? We gotta do the ring flip, and we look for things that were also axial with the bromine, the H's that were axial with the bromine. This was for sure an E2 mechanism. Right, we have a strong base with a negative charge. What if I wanted to do E1?
What's the base though?
So I'm just telling you it's going to be an E1 reaction. Doesn't matter what the base is. It's going to be E1. How many products would you get? Does it, if you have E1, if it's an E1 reaction, does it matter if the bromine's anti-periplanar anymore? So could you have more than one product then? Right. Where would you? What other product would you have?
1 to 6.
So you probably still have this product, right? There'll also be a double bond between 2 and 3. That's right. So in E2, since it all happens at once, we need the H and the Br to be trans, or to be diaxial. But in E1, this becomes a carbocation. And then,
Instead of the tungsten?
so yeah, so, right. So if it forms a carbocation though, right, yes, it could rearrange, but just humor me that, right, that because it's E1, the point is, does it matter if things are anti-periplanar for E1? No. Right? Yes, so you'll do rearrangements, you do all sorts of stuff. But the major point here is E1, does it need to be anti-periplanar? Absolutely not. That's the major point, that's what I was trying to get across. Okay, so I have a molecule here. It's an alkyl halide, so the first thing we do with all these reactions, before we look at anything else, we say, what kind of alkyl halide is this? Right, so what kind of alkyl halide is this? Just secondary, right? Nothing else. So then we draw out SN2, SN1. That's not right. Oh, my problem. It's not promising to be that sweet now. It's okay. We'll keep going. E2, E1. So can we eliminate any possibilities of the secondary alkyl halide? Which ones can we eliminate? We can eliminate SN1 and E1. Why? Has to be a tertiary or a allylic or benzoic, and that's not this case, right? We don't form carbocations unless they're really stable, right? So can we tell from this if it's going to be SN2 or E2? There's beta hydrogen, so, right? SN2, just worry about, is it secondary or primary, it still works. At E2, we need to make sure we have beta hydrogens. Are there beta hydrogens? Sure are. Let's number the carbons. 4, 6. I should. Oh, it should be. You should hear it. You should hear my voice in your head saying, "Number your carbons." And the first thing we of course do is number our carbons. No. All right. So our carbons are now so numbered. So we can look at this and say E2. We need to have beta hydrogens right now. Are there beta hydrogens? Which carbon has beta hydrogens? Carbon 4 does. Good. How many types of beta hydrogens are there? So how many types of alkenes can you form? There we go. Okay. But from this point, can we decide if it's SN2 or E2? No, we need more information, right? I mean, I can give you a problem like this and just say, explain to me how you pick, show me how you pick it, right? So now let's see, what are we going to throw at you? They're ethyl groups. This is ethyl. This is triethylamine. Kind of looks like the thing from the Matrix. Triethylamine. So yep, here we are. Triethylamine. Is triethylamine gonna be? What are we gonna do with triethylamine? It's pretty bulky, right? Would we say this is bulky? So if it's bulky, what's that going to hinder? E2 or SN2 more? It's going to bother SN2 more, right? So having a bulky base favors E2, right? Because SN2, you need that backside attack. So we're going to get a bulky base. We favor E2. And where we need to have the H is there. The electrons come all the way around. there, there. And our final product, the alkenes where? Between 3 and 4. Good. You number you don't number it wrong. The other thing, if you number carbons, so like it's awesome. I see a lot of people number carbons in their starting materials, but then they don't number in the products. So what's the point then, right? Or they number the carbons in the products, but not in the starting materials. It's like, what's the point, right? So 1, 2. It's a way to check to make sure you didn't lose a carbon, right? We talked about where we want the bond to be. 8. Does this look right, product? This is even better, right? So maybe this is even if I gave you a small base, maybe this is a better product. Why would this be why is this a good product? Yep.
But don't you need a stronger base for E2 to happen?
I just told you've already eliminated it. It can't be if there's gonna be a reaction. This is all you got. I mean, it'll work. This base. That base is strong enough. Nitrogen is strong enough. But right, if you've already eliminated things, I'm telling you a reaction is going to take place. Tell me your best idea of what reaction would take place.
So
a retrosynthetic problem would be, they're saying you're starting with this. And you need to get to these 2 products. 2? Ugh. Ugh.
Multiple choice.
2. Oh, for the love of God. It's over. We're done. Boom. Okay. So you gotta start with an alkyne, and you gotta make this ether with a bromine all of a sudden. Right? What's the first thing you should do? Alright. 1, 2, 3. And sometimes you'll say, well, how do I number the carbons in the product? So one of the things you can kind of look for, the pi bond is kind of where the action's happening, right? That's where we've done reactions before. So you can probably guess that the pi bond was here, right? Because all of a sudden there's bromine in this ether, right? So the pi bond was probably here. So when we number our carbons, we can number this as 1, 2, 3, right? So we kind of know that between 2 and 3, where's the pi bond was at? Because that's where the new stuff's at. That makes sense that they're there. But it looks like we've also added, have we added more carbons? Yeah. 4, 5, and 6. So we've added, so not only, what have we added? We've added bromine and OCH3. We've also added how many carbons? 3 carbons, right? So somewhere along the line we have to add carbons. And you guys have only learned one way to add carbons, really, besides the organometallic stuff, right? Remember how we make carbon-carbon bonds? What do we have to make them with? Perfect. So let's go back one step. Friedel-Crafts, besides any electrophilic aromatic substitution, this is last semester. If you had an alkyne, could you add more carbons to an alkyne?
Yeah, there was something.
There was something about that? It's true, yeah. So that's, yeah, right? Okay. So keep that in the back of your mind, right? Because we have an alkyne here and we have to add carbon, so, right? Take one step back. If we just take one step back, let's focus on this bromine and this OCH3. How can we add bromines? What starting material do usually bromines have to come from? Alkenes, right? They come from alkenes, right? So the alkene this came from, what relationship does this CH3 and this isopropyl have to each other? Are they cis or trans? They're cis, so we should draw them cis. And this H and this H are cis to each other. Okay, that's cool. So here, okay so far? Now we have a cis alkene. What star material do cis alkenes come from? Cis alkenes come from alkynes. Oh, never mind carbons. 1, 2. Sorry, Lucy. You're right. 5, 6. Okay. So 1, 2, 3, 4, 5, 6. Everybody see that alkyne now? All right, haven't thought about any reagents yet. All right, but one way to make a cis alkene is from an alkyne. Right? Now, can we go from here to here? Can we take this alkyne and make it from this 3-piece? Yes, we can. Good. So now we got to go forward, right? So what reagents am I going to need to add these carbons to this alkyne? Take off the H, so I'm going to need Na, NH2, strong base. And then what electrophile am I going to have to add? Can't be a carbocation. It's going to have to be a... How many carbons? 3. Right? Because this would be carbon 4, this would be 5, and this would be 6. Right? So you need 2 propane. 2 bromopropane.
Do we have to draw it or do we just write it out?
Draw it. What, write out like this carbon piece, or what are we going to write out?
Well, like instead of drawing like C. Yeah.
Just draw like CH3, CH2, brom.
Yeah.
Draw. You could try. Yeah, go for it. If it works, it works. If it works for you, go for it. Sure. Okay, so that gets us to the alkyne, and then now we want to do here. Oops. We want to do a cis hydrogenation. What reagents does that? Lin-Lars. Right, Lin-Lars. Lin-Lars with a little H2, right? Sure. Okay, good. That gets us to a cis alkene. If we want to make a trans alkene, what would we use?
Lithium.
Sodium and NH3. And don't forget, remember, I don't know why we confuse this so much. For next year, we're just doing lithium. I'm not going to talk about sodium. I'm just going to say it's lithium. To get a trans one, remember the reagents are usually sodium, metal, and then NH3, liquid. Right, versus NaNH2. But since you guys are never going to run that reaction, I can just call it lithium. But who cares? Who cares? We're on tape. All right, final step. Final step here. Now we need to get the bromine and this OCH3. Appears to be, what kind of relationship are the bromine and OCH3 to each other here? They trans. How do I do that? BR2. Do I need anything else? CH3 OH. Good. That's my solvent. Would I also get the enantiomer of this? Right? Is there any preference to the bromine? Right? Make the bromonium ion. Does it care whether it comes from the top of the alkene or the bottom? So I get the enantiomers. I get both products. But this is what I'd ask you. So something like this could be a problem for you guys.
It'd be the exact same problem.
So let's talk about fluorine as a leaving group. Okay, fluorine as a leaving group is one of our ways to get a non-Zaitsev product, so a less substituted product. So let's see. Let's put F here. Right? So we got an alkyl halide. Right? First thing we do. Number of carbons. 2, 3. Should I say that every so often during the test tomorrow? First thing we do. Right? Okay, so we numbered our carbons. Now we need to label what kind of alkyl halide is this? Secondary alkyl halide. Good. All right. SN2, SN1, E2, E1. Secondary alkyl halide, can we eliminate any of these? E1 and right? Because we're not going to form a carbocation and a secondary carbon. Good. Can I eliminate SN2 or E2 at this point? SN2 is probably less likely because, right, fluorine's such a bad leaving group. Why? Because how small, and it can't spread out its charge, right? So it's like a little ball of charge, right? So really, I mean, in this case, I will add in, right? Let's say this is your base, butoxide, right? So it's a strong base, negative charge, but what else about this base? It's pretty bulky, right? So we're going to probably thinking less about SN2 and more about E2. So if we know it's E2, what do we do with eliminations? We need to label what? Beta hydrogens, right? So which carbons have beta hydrogens? 1 and 3. So let's put the H's there. Beta. Good. So how many types of beta hydrogens do we have? So how many types of products are possible? 2. But because it's fluorine, it's a little different mechanism, remember? So instead of getting the most substituted alkene, fluorine, we actually grab the least substituted beta hydrogen.
Wouldn't it already bond there because it's a tertiary?
It's a tertiary base, but is that tertiary alkyl halide? To get the non-Zaitsev, you need a tertiary alkyl halide and a big bulky base. This is only secondary. So the first step here is actually not an elimination. The first step is we're going to have a negative charge on carbon 1. Right? Because fluorine's such a poor leaving group, instead of it all happening at once, the negative charge just builds up on a carbon. And if the negative charge is forced to build up, which type of carbon would it rather build up on? More substituted or less substituted? Less substituted because of hyperconjugation, right? Just the opposite, right? A negative charge hates hyperconjugation, so I want a carbon that has less hyperconjugation. And 1 has less hyperconjugation than 3. Because fluorine's such a bad leaving group. Instead of just all happening at once, fluorine lets this negative charge build up first. And so now here come the electrons finally. And it kicks out F. Right? So that CH bond broke. Yep, we built up a charge on carbon 1.
By just putting electrons.
Just put electrons on carbon 1. And if we put electrons on a carbon, if we put a negative charge on a carbon, we want the least substituted carbon because of hyperconjugation. It's bad for it. Finally, it breaks. And now we have a pi bond between carbons 1 and 2. And another way to make a non-Zaitsev product, right? A less substituted product, just based on the leaving group, because we go through this kind of alternative mechanism.
Fluorine technically has 2 steps all the time.
So fluorine technically has 2 steps all the time. Yes, there's 2 right. So how do we understand nucleophiles or bases, right? So understanding nukes, and of course bases are a particular type of nucleophile, right? So what are the 3 things we look at for understanding nucleophiles? Charge,
Rows and columns.
rows, and periods, right? The columns, yes, sure. So each one of these ideas has a main point to it. So charge is the easiest one. How do you tell if something's a better nucleophile? It has a negative charge, right? Negative charge, better nuke. Easy enough, right? All right, you can think of OH minus versus water, right? Easy. Right? Something that's a negative charge is, for all intents and purposes, going to be a better nucleophile than something that doesn't. Something that has a positive charge, is that a good nucleophile? No, it's not a nucleophile. Be careful. I'll throw you the true value tumbler. Is the name of the knuckleball I threw? Okay.
You just make that up?
Rows, what's the most important thing? Electronegativity, right? So For rhos, it's more about electronegativity. So as you go across negativity, whatever. So as you go across a row, what happens? So classic one we compared, let's compare OH minus versus F minus. Which one's the better nucleophile? OH minus or F minus? Why? Less electronegative, more willing to give up its electrons. That's right. So OH minus, just like it is up here, is a better nucleophile. But that principle across a row is based on electronegativity. All right? Now, periods. As you go down the period, what happens, what changes? What's the big principle? Size changes, right? So as you get bigger, right? So let's compare Cl minus versus Br minus. So which one of these is bigger? So which one do you think is more willing to give up its electrons? Br, just because it's bigger. So there's a so this is a tougher one, right? What else is going to come into play with the periods? The solvent choice also makes a difference here, right? So it depends on the solvent, right? So to a certain extent, depends on solvent. No, it really depends on the solvent, right? Depends on the solvent. So if I'm going to tell you it's a protic solvent, which would be a better nucleophile? Cl minus or Br minus? So protic solvent means what? Can it hydrogen bond with itself, right? So if I'm a nucleophile, do I want to be hydrogen bonded to? No. Which one of these guys is going to be less hydrogen bonded to? Because it's bigger. So in protic solvents, you want bigger is better, right? You can't be surrounded by the solvent. In an aprotic solvent, now you can't do hydrogen bonding, right? Now who's going to be the better nucleophile? Cl minus or Br minus? Now it's going to be Cl minus, right? For exactly some of the same reasons we talked about, right? Br minus is more stable because it's bigger, right? Cl minus usually forms a stronger bond to carbon, perhaps, right? More similar in size, more orbital overlap. But in aprotic solvents, you don't have to worry about the nucleophile being surrounded like we do in protic solvents. So the smaller is actually better.